Now let's talk about the variation with time and with seasons of the Earth's radiation. We'll begin with something very elementary. The Earth's axis is tilted with respect to the plane around which it orbits the Sun, and for that reason the solar incident angle varies over the course of a year. This diagram, for example, shows the incident sunlight during southern hemisphere summer. The amount of radiation that intercepts the Earth's surface per unit area varies with the cosine of the solar zenith angle. The solar zenith angle is simply the angle that the sun's rays make with the local vertical. So at the summer solstice, at 23.5 degrees south latitude, the Tropic of Capricorn, the solar zenith angle is 0. The cosine of the solar zenith angle is 1. The sun's rays are perpendicular to the surface of the Earth. But in the northern hemisphere, the sun's rays intercept the Earth at an angle, and at the Arctic Circle, that angle is essentially 90 degrees. There is no sunlight intercepted north of the Arctic Circle at the winter solstice in the northern hemisphere.
This diagram shows the distribution with time of year and latitude of the total incoming solar radiation at the top of the atmosphere. Let's begin by looking at the equinoxes around the end of March here and the end of September here. We see that during the equinoxes, solar radiation is distributed fairly symmetrically in latitude about the equator, dropping off toward both poles. On the contrary, at the solstices, for example, the northern hemisphere summer solstice here, there is very little gradient of the solar radiation between the North Pole and the equator. And of course, in the southern hemisphere summer solstice at the end of December, likewise, very little gradient between the South Pole and the equator. In fact, the peak solar radiation at the solstices occurs at the poles. In the winter hemisphere, on the other hand, there are large gradients in solar radiation between the winter pole, where of course there is none, and the equator.
If we look at the average with longitude of the incident solar radiation in the annual average given by this solid line, and at the two solstices, the northern hemisphere winter solstice on the 21st of December and the northern hemisphere summer solstice on the 21st of June, we see some interesting features. In the annual average, of course, solar radiation peaks at the equator and falls off toward both hemispheres. You'll notice something interesting if you look closely. In the southern hemisphere, the minimum radiation at the South Pole is about 150 watts per meter squared. But in the northern hemisphere, at the North Pole, the annual average radiation is slightly less than this. Why the asymmetry? This has to do with the fact that the Earth's orbit is elliptic, and in the era in which we live, the Earth is actually further away from the sun during northern hemisphere summer than it is during northern hemisphere winter. This means that in the summertime, there's slightly less radiation coming into the North Pole than in the southern hemisphere summer. Now, if we look at the solstices, what we see is equally interesting. Very strong gradients of incident solar radiation between about 60 degrees latitude and the equator in the winter hemisphere, and very small gradients of incident solar radiation in the summer hemisphere from about 30 degrees poleward. This is true in both seasons. Here again, we see the asymmetry, more radiation coming into the South Pole on the 21st of December than incident on the North Pole at the 21st of June due to the ellipticity of the Earth's orbit. Here is a sequence of maps of the surface albedo of the planet spanning the months of the year. This is for a particular year, 2004. The white on this diagram is snow and ice. So where there is snow and ice, there's very high albedo. But bear in mind that some of this high albedo occurs during a time of the year when there's very little incident sunlight. So what really matters is high albedo where there is much incident sunlight. Notice also that desert regions of the planet, such as the Sahara Desert here, the Atacama Desert, the deserts of the southwest US and Mexico, are highly reflective at all times of the year. A lot of the variation in albedo due to snow and ice occurs over the northern hemisphere continent simply because there's much more land at high latitudes in the northern hemisphere. This diagram illustrates the difference between the net absorbed radiation, that is the difference between absorbed solar radiation and emitted long-wave radiation, during the northern hemisphere winter on the left and during the northern hemisphere summer on the right. So you see a huge seasonal migration in the Earth's radiation budget, with the winter hemisphere being a net emitter of radiation and the summer hemisphere in general being a net absorber of radiation. But there are some anomalies, like the Sahara Desert here doesn't absorb in the net much radiation owing to its high surface albedo. Here is another sequence of maps showing the seasonal migration of the net radiation budget of the Earth as measured from satellites. You can see the north-south migration of the regions of high absorption and emission of radiation. Finally, let's have a look at some measure of the temporal variability of terrestrial radiation. This is the mean and standard deviation of the outgoing long-wave radiation as measured by satellite during the period 1979 to 1995. This top chart shows the average outgoing long-wave radiation, once again showing maximum over the dry regions of the subtropics, where there aren't many clouds and not much water vapor to absorb the outgoing radiation, with local minima around the equator, particularly over the maritime continent, Indonesia, and over South America and Africa. The bottom chart shows the standard deviation away from this mean, showing that the standard deviation tends to be large, where the mean outgoing long-wave radiation itself is small. That is where there are a lot of clouds and water vapor, but there are some interesting variations on this theme. So while the minimum outgoing long-wave radiation is over in Indonesia, the maximum in the fluctuations of that are somewhat further east, probably owing to forms of tropical waves and other oscillations that cause large standard deviation over the western tropical Pacific. Let's summarize this entire section of the course. First of all, climate variations involve principally the Earth's troposphere and stratosphere. Higher levels of the atmosphere are not thought to be terribly important for climate. Seasonal temperature variations are most prominent over high northern latitude continents. Over 97% of the mass of the atmosphere is comprised of molecular nitrogen and oxygen, but trace amounts of other gases, particularly water vapor, carbon dioxide, ozone, and methane, together with clouds, are responsible for a powerful greenhouse effect that keeps the Earth's atmosphere and surface much warmer than it would otherwise be. This greenhouse effect occurs because the surface must get hot enough to radiate away not only the sunlight it absorbs, but the infrared back radiation it receives from the atmosphere and the clouds within it. Carbon dioxide and methane, both long-lived greenhouse gases, have been increasing since the mid-19th century, and they also show a seasonal cycle. Ocean and atmospheric currents transport heat away from the tropics and toward the poles and upset the local radiative balance, so that on average, the tropics absorb more radiation than they emit to space, while high latitudes emit more radiation than they absorb.